we're supposed to add this series, which is not an easy thing to do. But if we can find the function that this Taylor series represent, then hopefully we can evaluate that function. So let's write it down. See, 1/3 keeps happening over and over. So we'll say f of x is x minus, this is x, and this is x cubed, right? For some reason, this exponent is missing. What is going on? This exponent is missing in these things, right? Oh, I see. Let's see what's going on. Let's write it like this. X cubed over 3. And if we're doing this, right? So if I cube it, then do you agree that I get this thingy back? And then if I take x to the 5th power, and then we take over 5. Do you see that's 45 with this thingy? Oh yeah, that's a clever trick now, isn't it? And the next one will be x to the 7th over 7, and dot, dot, dot. And then remember, whatever we do, we need to evaluate this thing at f of 1/3. Okay, good. Now, this is so much easier to see. Have we seen that before somewhere? Well, I think we have done this type before. Don't you want to differentiate? If you differentiate, that 5 cancels, this 7 cancels this 7. You know what I'm saying? And this is a good microwave technique. I might have built it from the scratch, but since we have this, we'll just work with this. So first thing we want to do is we want to differentiate so that things get easier. So this becomes 1, this becomes minus x squared, this becomes plus x to the 4th, and then minus x to the 6th, and dot, dot, dot. Look, this looks like geometric series now, doesn't it? Yeah. Okay. Do we know this thing adds up to 1/1 minus negative x squared, or you want me to review the summation? Because you cannot do this on the test unless it's multiple choice. Do you want to see the summation of geometric series one more time? Yeah, let's do that. And that justification happens like this. Okay. We have to first call it Pn of x. Okay, we have to always terminate it. So that thing looks like 1 minus x squared plus x to the 4th, dot, dot, dot. And then, what should we call it? We'll just call it 2n. Although it's kind of misleading, but you know what I'm saying. The whole point is we just take n approaching infinity. So this is really twice as much as our usual notation, but I think this will work. And then Pn, and we multiply the common ratio on both sides. So we multiply negative x squared. So this becomes negative x squared. This becomes plus x to the 4th. Next one becomes x to the 6th, dot, dot, dot. And this becomes 2n plus 2. Good. Now we subtract. So we subtract, so this is 1 minus negative x squared, common factor, Pn. And everything cancels except the first one and the last one, which I will have to write it as plus or minus, because I don't know which is which. So far so good. Divide. So Pn of x is equal to 1 plus or minus x to the 2n plus 2 over 1 plus x squared. With me? And that is our f prime at the moment. So f prime of x is the limit of Pn as n approaching infinity. And then we want this to die, correct? That thingy. Good. So we want this to die and become this, and this comes with a condition. What is the condition? We don't need a condition here, but good to know. Interval of convergence, so as a review. What is the condition?
Absolute value of
Yes, has to be strictly less than 1. Good? Good? Well, you can say x squared, but that's still same thing, isn't it? So our interval of convergence here needs to be from -1 to +1. This is a nice review, isn't it? And we are evaluating this at 1/√3. So 1/√3 is okay. It's definitely between -1 and +1 now, isn't it? So we are more than okay, right? Otherwise, if the thingy that we are trying to evaluate falls outside of this interval of convergence, then we cannot add this. This scheme falls apart. Good? Okay, now, so we are back here. Now, we have to integrate this thing back, eh? So let's integrate it. So if we integrate it, f of x is equal to, can somebody tell me what the antiderivative of this is now? Or you want me to show you that as well? Tricks up. Review number 2 within this problem. This is an excellent problem. Y'all know this is it. Yeah, do you all know this is inverse tangent, or does anybody want to see that integration technique? Put your hands, last chance. Okay, then, assuming everybody knows this one, and then we have to figure out C, right? So we plug in 0, okay? I mean, plug in where? We plug it in here, right? Our original series, okay? So there's, then f of x becomes 0 on the left-hand side, and inverse tangent of 0 is a 0 plus c. So that tells you c is equal to 0, eh? So finally, our function is equal to inverse tangent of x. Good? Now, then, remember what we were set out to do? We're supposed to evaluate this thing at 1/√3. Ooh, since from the past. Tell me you still got this. What is the inverse tangent of 1/√3? Also known as √3/3.
Pi/6.
Thank you. Wow, that was great. Our reputation of this high school is still intact. Where's the WASC committee member when we need them? Right, they're gonna walk into the other period, I'm sure. Okay, so that was that. Alrighty, shall we do number 46 now? Yeah, let's do 46. Okay, we just need to, what was the problem again? Figure out whether this is convergent or not, right? I think that was it. How would you figure this thing? What kind of, usually you want to do ratio test, but something tells me you don't want to do ratio test of this one, right? Something tells me this ratio ain't gonna be pretty. So ratio test fails. Any good idea? Come on. Okay, when
Test.
integral test is the way to go, okay? So let's compare this thing to the integral of 1/x ln x squared, right? dx. And whether to write 2 here, or it depends on the direction of the inequality. If it's this way, this needs to be 1 greater, so either change that to 3 or we can change this to 1. No, we don't want to change this to 1 because ln 1 is 0, so you have to change that to 3. If the direction is that way, then we don't change it. Do we know the indexing and this thing? because many of you lost a point on the quiz number 1 for not writing this correctly. But for now, we'll just evaluate this integral and see whether this thing converges or not, right? It depends on the convergence of this very integral. So let's go. And some of you are still substituting infinities around, and I cannot believe it. Actually, somebody did it on the take-home test too. Like, whoa. Proper integral, people. Proper integral. So 2 to b. And then what is this thing? How do you wanna, do you see the technique of integration? Somebody say it.
Substitution.
Yeah. Let me just write it like this. Do you guys all see it now? Do you want me to do you see this is u and that whole thing is your du? You want to do u sub in your head, or you want me to physically write down what u and du is? Your choice. Okay, who's the owner of this problem? You decide.
Yeah, can you do it by hand and show us?
Okay, so we'll let u to be ln x, and du is equal to 1 over x dx. Then do you see that thingy right there is your u, and this thingy is your du. Huh. How about that? Good. So what happens is, now limit p approaching infinity. So this thingy becomes u to the -2 du, like that, eh? Do we want to change this limits or not? Let's change it, might as well, right? So b is approaching infinity and u. So when x is equal to 2, this lower limit becomes ln 2, right? You know what I'm saying? And the upper limit now becomes ln b then, eh? Not that hard. Okay, let's go. And limit b approaching infinity. This is u to the -1, isn't it? So this is u to the -1, therefore negative sign from ln 2 to ln b. That ln looks nice, okay. Use plumbing professor and substitute this one first. Yeah, let's do that. So b approaching infinity of 1 over ln 2 minus 1 over ln b. 8. And then we take a limit and this dies. This is convergent after all. So this whole thing becomes 1 over ln 2. Good. Then finally, we have to establish the inequality, right? So we want the inequality to be this way, so our series is less than some finite number, then we have to change that to 3. You get it? Would you like to see that rectangle one last time, or are we good? Okay. And then it doesn't care, because even if you add the first term back, then your series is this thingy plus when n is equal to 2. You get it? But this proves that series is convergent. Let us write therefore convergent. Good. Alrighty. Any questions before we go to 56? Okay. 56 is an excellent question. Now we are given some kind of polynomial, fourth order. Okay, this is a Taylor polynomial and evaluated at center 4. Okay, and fs derivatives of infinite orders. F of 4 and f of... and how do you do such a thing, right? Okay, this is why I relieved you from doing it the long way, right? I mean, we could still do it the long way, But according to our formula, this is part A, Taylor series formula. We first evaluate it at the center, or we'll write it as 4 in this case, right? Center. And the next one is f prime of 4 over 1 factorial. And the next one is f double prime of 4 over 2 factorial. And f triple prime of 4 over 3 factorial. And f fourth derivative evaluated 4 over 4 factorial. You know what? I'm done because I forgot x's. Did I say that on the recording? X minus 4. I forgot these guys. Yeah, see, this is why the long way is better. X minus 4 squared. Dang it. I just got carried away. For the record, I just got carried away. And then x minus 4 to the 4th power, and dot, dot, dot. Good? Right, this was the forbidden formula, which I kind of released it to you so you can use. Let's compare this thingy to what we have here, okay? So we need to find f of 4. Oh, this and that, right? So do you see that? Therefore, f of 4 must be 7. We are comparing this term to that term. You get it? Okay, and then we need to find out f triple prime of 4. F triple prime, we need to compare this term to that term, correct? Say yes.
Yeah.
Okay, now, so that's -2. So we also know that f triple prime over 3 factorial is equal to -2. You know what I'm saying? And that triple prime of 4. Oh my God, what are you doing today? So f triple prime of 4 is equal to 6 times 2, -12. How about that? Beauty? I know that's a clever technique now, isn't it? So formula could be useful once in a while. Okay. Should we do B as well? Might as well, right? Yeah, let's do it. B. So second order of this f prime. So we just take a derivative of this, well, not this, that. Okay? But second order, so we stop after second order. So first one dies, this one becomes -3. I'm gonna display it on the other screen and then I will look at it because it's back and forth is becoming a little bit of hassle. This is 56, okay, got it. You guys have better memory, so remember this. We are taking a derivative of this, so f prime of 4, x, is approximately equal to, because we're going to cut it off at second order. Okay, is first one dies, so we have -3 and plus 10 x minus 4 and minus, who dies? 6 x minus 4 squared. Good. What I did was I just took the derivative of these guys and cut it off after this term because that becomes a second order. Good. Therefore, squiggle equal to and no dot dot dot. You with me? Okay, somebody have a calculator standing by and we are supposed to approximate 4.3. So f prime of 4.3 is approximately equal to, somebody substitute 0.3 to 4.3 here and tell me what that thing becomes. And I'm going to move on to C while you run that number.
Negative 0.54.
Negative 0.54. Exact? Yeah, I think so. Huh? Okay, good. Thank you. And then C. Fourth order Taylor polynomial for okay, so g of x is equal to antiderivative 4 through x of f of t dt. Okay. Squiggly equal to, there's a reason I put squiggly equal to, and then we copy this polynomial down, and I'm looking at the other screen. That must be 7 minus 3, x minus 4, plus 5, x minus 4 square, and we want fourth order, right? Yeah, so we need one more term. Minus 2, x minus 4 cubed, cut it off, dx. Therefore, squiggle equal to here. You get it? Any questions? Any confusion? Why this is squiggle equal to? Okay, then now we evaluate. So that thing is, now we'll evaluate in terms of x minus 4. So 7 x minus 4. Oh, we are supposed to write t. God, mathematicians will have a heart attack if we, I mean, it's the same thing, but this is a no-no. Mathematicians everywhere cannot really see this, right? Then we can substitute x here. We cannot have x here and x in here. You know what I'm saying? I don't know why they care about these things, but they do. So t minus 4 plus, and this thingy minus 3 over 2, t minus 4 square plus, and this thing becomes cubed, so 5 over 3, t minus 4. What is wrong with you today? Minus 4 cubed, and one more, this becomes 4, so negative 1/2, t minus 4 to the 4th power, and from 4 to x. Still with me? Okay, once you substitute 4, all of these things die. So that's at least nice. So we just need to worry about x. So the whole thing becomes, now back to x. How about that? Good? Now, notice that I have approximately equal to here and straight equal to here, right? Don't be putting approximately here. What that means is this line is exactly same as that line. This line is exactly same as this line. This is not exactly same as that thing. Is what that means, okay? This is same as you're linking it sideways forever, really extra long. All good? Okay, now lastly, can exact value of 3, f of 3 be determined? Okay, well, it really depends on whether we can see the pattern and figure this out, except we don't know the rest of there's no apparent pattern, and then we cannot really know what the entire series is. We have to have the entire series before we can even think about exact, you know what I'm saying? And there's no pattern, there's no series, there's no formula given to us, so answer to D is no. And then I just verbally explain, there are you need the infinite terms, and then we have to recognize it as some kind of function, that as we did earlier today. So no, we cannot. Good. Okay, now they wanted a 3, yeah, 3. Wait, one last time. If you put 3 here, this becomes -1, -1. Yeah, it's an alternating series, except we don't have enough pattern to add those. Okay, any question? Well done, we'll do 58. This is a nice recording session, okay? So 58, we have such a thing. First 4 terms of Taylor series, okay. Well, this we shall definitely microwave, eh? And do you remember this thingy? 1 over 1 minus x thingy. This is basically summation, geometric series summation formula, isn't it? And this is 1 plus x squared plus x cubed plus dot dot dot. Good? So all we have to do is replace x with 2x, eh? Therefore 1 over 1 minus 2x is equal to now 1 plus 2x plus 2x squared plus 2x cubed. 2x cubed, not 2x3. That too looks ugly. And then dot dot dot. Good? Okay, now interval of convergence. Okay, now we have to be careful. Isn't that -1 to 1? No. Why not? See, this thingy has an interval of convergence from -1 to 1, correct? But we replace, this is a scaling effect now, isn't it? Once you replace x with a negative x, do we shrink it or do we stretch it? Which way are we scaling?
-half to half.
-half to +half is the correct one now, isn't it? Right? You want to do ratio test just to confirm it? Yeah, let's do that, right? Whoa, what just happened? Let's just do a ratio test to confirm that belief. So ratio test, limit of n approaching infinity of, we have 2x to the nth power, right? So we have 2x to the n plus 1 power, right? Oh, we should have done nth root test. This would be the one that, you want to use nth root test. Too late now. It gives you the same thing. See, 2x. I should still write limit. Limit n approaching infinity of 2x. See, it gives you the same thing. And that thing is same as 2 times absolute value of x, and that needs to be less than 1. You know what I'm saying? So that tells you absolute value of x is less than half. Yeah, I'll just write it like that. Then we have that interval of convergence, right? Actually, we don't exactly know that because we haven't done the boundary. But can we not do the boundary and say, yeah, this is definitely it because the endpoint didn't include back then, right? Or do you want to see me testing this thing on the boundary as a review as well? How many of you want to review that? There's a test tomorrow after all, so if you want to see it, I will test the boundary, otherwise I'll just stop. That's your radius of convergence. Okay, let's just stop. Then your interval of convergence is -half to half, as we believed. I haven't tested the boundary yet, but from here, it didn't include back then, so it shouldn't include now. I mean, this is kind of like geometric series after all. You know what I'm saying? Okay, and C. Let's read C. So evaluate this at -1/4. And how many? Oh, so error, right? Not exceeding the percent. 1%. Okay? Okay, let's do the error analysis. So, do we need to? Oh, yeah, we have to figure this out. This was B. Was it C? Yeah. So C. F of -1/4, say. We have the function. This is our F, isn't it? So we plug it in. 1 over 1 minus 2 times -1/4. That's 2/3. Did I do that right? I think I did that right. You with me? Okay, now we have to figure out R sub n, right? At -1/4. We cannot do Lagrange error because we just microwave that thing. Suggestion. I will listen to your brilliant suggestion. How should we do the error of this thing when we don't have Lagrange error? Why don't I write down this error? Okay. So what term does it start with?
n+1.
n+1, right? So we have 2 times -1/4.
Alternating series error.
Oh yeah, right? And plus 2 times -1/4 and plus 2 and then dot dot dot, right? And then whatever this is their alternating series now, isn't it? Because either this is positive, negative, or this is negative, positive, negative. By putting -1/4 in, this whole thing becomes alternating series, doesn't it? So we can apply alternating series error, which is this term, right? So 2 times -1/4 to the n+1 power. Okay, let's evaluate that. So we can say R sub n of -1/4, absolute value, so we don't have to worry about that thingy, sign, is less than or equal to, I guess we'll just have to write it, right? 2 times 1/4, let's write it like this. 2 over 4 to the n+1. How about that? Good? Say yes. Okay, and that needs to be less than or equal to, what's 1%? Don't tell me it's just this, right? No, it's not this. That's not 1%. That is 0.01. 1% of what?
2/3.
1% of this. That's why they had us calculate this. 1% of 2/3. Okay, somebody run the calculator and tell me what this n value should be. N should be greater than equal to.
Wait, Mr. Kim, shouldn't the 2 have a n+1 on it? So it can just be like 1/2 to the n+1? Over on the Rn less than that.
Oh, what was I thinking, right? I can, yeah, this is just 1/2. 1 over 2 to the n+1 now, isn't it? Yeah, nice catch. That made the problem so much easier now, right? So n should be greater than or equal to? Oh, come on.
7.
7. Okay. So we have to run this thing up to 7's order. You get it? not 7 terms, 7th order, but I just thought about better way. There is one way that is better than this. Although AP is probably looking at alternating series error, but I thought about the better error. Can you think of it? What is the more accurate error than this one? The hint is, I know how to find the exact error. What? How can you find the exact error? I will let you stare at the series. Well, there's our series, right? This is our series. How can you find the exact error?
Geometric series?
Yeah, that's geometric series, isn't it? Oh my God, right? So we don't need this alternating series error. We have one better than that. Because remember, geometric series error is exact. Alternating series error is a big approximation. You know what I'm saying? So I'm gonna make a distinction. I'm gonna actually write down the title. Oh, this is going to make a great video. Okay, and write C here, and this is alternating series error. Okay, but we can use exact error. Which is geometric series. Okay, how do we find the geometric series error? Multiply both of this by whatever the nth term that we are trying to find, correct? Wait, n plus 1 term we are trying to find, correct? Okay, so let's multiply both sides of this by 2x to the n plus 1 term and see what happens. Space 2x to the n plus 1 term over 1 minus 2x is equal to, then first one becomes this. And then second one becomes 2x to the n plus 2 and 2x to the n plus 3 and dot dot dot. See, that's exactly this thingy, isn't it? Now, but if you notice, this is your error, isn't it? This is your R of n of x. You know what I'm saying? Oh, that was clever. So, question? So if we want to evaluate R of n at -1/4, wasn't it? Absolute value while we are at it. We can just substitute -1/4 in here. You get it? So we have 2 times -1/4 n plus 1 over 1 minus 2 times -1/4, like that. So this we can still simplify. Oh, and then absolute value around it. So this is still 1/2. So we have 1/2. Let me write it. Let's zoom in a little bit. 1 over 2 to the n plus 1 over, and this is 1 plus 1/2, eh? 3 over 2. Say yes. Okay, so this is same as 2/3 of 2 to the 1 over 2 to the n plus 1. Good. We can cancel this, don't cancel it, but I don't want to cancel it, and the reason I don't want to cancel it is that needs to be less than half, less than or equal to 1% of 2/3. We have 2/3 here and 2/3 here. Ain't that nice? So what we end up happening is 1 over 2 to the n plus 1 should be less than 1 over 100. And let's compare that answer with what we had here, right? So we gained that factor. Somebody punch the calculator and tell me what this is. Oh, come on, people. Class is almost over, so
6.
6. So we can do one better. 7 will do, but 6 is better, isn't it? I mean, if you're using a computer, the computer doesn't really care, but still, we're trying to be a little more efficient. That was a great review, wasn't it? Okay. Let's add this series up. Looks pretty daunting, right? But then, if you think about it, there's a 2/3 to the nth power, right? So the scheme is this. We have done this kind of problem before. Instead of 2/3, if we write it as f of x, wrong color. If we write it as f of x instead of 2/3, then we can recognize this. We can find the function that this Taylor series represents. Then we can manipulate this. You know what I'm saying? So let's just write it. This is x, okay, and then minus, do you see this is x squared, 2/3, and then the other one becomes 1/2. If x is 2/3, do you see that gives you this? Is it difficult to see? You want me to write it at the 2/3 first? Or can you see it? And then the next one is plus, and then we have 2/3 q, and this is, you know what I'm saying? And then minus, next one is 1/4. Actually, this one is a giveaway, so we don't have to write it. Of course, you can see it. And then dot, dot, dot. So far, so good. And then later, much later, down here, we need to evaluate this thing at 2/3. You know what I'm saying? So that's our goal. Now, once you write it like that, you want to differentiate to cancel these things, the coefficients, correct? So let's differentiate it. So f prime of x, this becomes 1, this becomes minus x, this becomes, did I write 2/3 in there? Oh my God, I switched over to 2/3. Hold on. This is x cubed. I'm gonna rewrite the whole thing. This is x cubed and minus 1/4 x to the 4th power and dot, dot, dot is what I wanted to write. So this thing becomes plus x squared and this thing becomes minus x cubed and dot, 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 correct? Wow, we know how to add that thingy. It's geometric series, isn't it? Do we all know the summation of geometric series? Or you want me to show you how to do this one last time? Because you're not allowed to just do this tomorrow. Okay. So if you want to review summation of geometric series technique, show your virtual hand, last chance. Ne? Okay, 2 people. Okay, let's learn how to add geometric series, shall we? Okay, let's review here. So we have to call it Pn of x. You have to always terminate and you add. So what we have is 1 minus x plus x squared dot, 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 plus or minus x to the nth power, nth order polynomial. Okay, then we multiply both sides by the common ratio, which is negative x, So this becomes negative x plus x squared minus x cubed dot, 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 plus or minus x to the n plus 1, Then we subtract. So this becomes 1 minus negative x, common factor Pn of x, And then everything else cancels except for the first term and the last term. Good? Say yes. Now we divide by 1 plus x, so Pn of x, it becomes 1 plus or minus x to the n plus 1 over n plus x, 1 plus x. Now we are calling that sum f prime of x. So now our f prime of x is limit of Pn of x as n approaching infinity. Good. And we want this numerator to die. I mean this x term to be die, and we didn't have to do it here, but what is the interval of convergence? What is the condition of geometric series summation? This comes with a some condition. What was it?
Less than 1.
Less than 1, right? So that tells you the interval of convergence between 1 and -1. You get it? Okay, so I'm going to push this guy down. So your interval of convergence is between -1 and +1. And it's good to know because we are evaluating this at 2/3. You know what I'm saying? And 2/3 is within this interval of convergence. So this technique will work. So you always think, remember that quiz 2 that I inadvertently gave you something that's outside, I mean that bad things happen. So this, none of the techniques will work if the series is divergent. So you always think interval of convergence, even if you're not required, okay? So now we're back, so we're here, good? Now we have to integrate this in order to find our f of x original back. So let's integrate, because this is f prime of x, so this, is it ln? And are we sure? Because that -10-point penalty still applies, it'll always apply. Okay, then initial condition. So at x is equal to 0, where are we substituting 0 to? The right hand side becomes ln 1 plus c, and ln 1 is 0, but what do you put here? Where are we substituting this x is equal to 0 to? Oh, come on, people. What is our function? Well, isn't that what we're trying to find? No, this, you get it? We're substituting 0 here, 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 and everywhere. So entire value series becomes 0. You get it? And that tells you your c is equal to 0. You know what I'm saying? So your f of x is just ln 1 plus x. And then, of course, you are supposed to evaluate this at 2/3 because the original problem had 2/3 in it instead of x, right? We just created f in order to manipulate and add this up. So that is ln of 2/3 here, so 5/3. How about that? Good. Do you love it? What is there not to love, right? So we'll look at number 60 now. Did I overpass it? Yeah, number 60. Okay, I'm gonna push this down. Okay. Now we write the first 4 terms and the general term of Taylor series. Oh, this is, we can microwave this, right? Or do you want to do it the long way? Well, that depends on whether we need a Lagrange error at the end. And then result from by and evaluated computer number difference from. Oh, we do need Lagrange error, right? Shall we do it the long way or semi-long way? Because I relieved you from that burden of doing it the long way. You know what I'm saying? Okay, then maybe we'll do a semi-long way, or we can still microwave and figure there is a way. But let's do it the semi-long way as a practice, okay? So f of x, this is a, so f of x is 1 over x minus 2. Good? Oh, why am I writing like that? Let's write it like this. X minus 2 to the negative 1. How's that? Good? So f prime, f of, and then we are centering this at 3. So we are supposed to substitute 3. You know what I'm saying? Because a semi-short way could be confusing, so, and then the other side is a naught plus a1 x minus 3. We are still imagining that, right? Here 2, the other side. And if you plug in 3, this thing becomes 1, doesn't it? Say yes. So that tells you a naught is equal to 1. Do you believe it? You want me to show it to you the long way, or do you get it? We are kind of using the Taylor series formula. And then we take a derivative. So this becomes negative, and then x minus 2, negative 2. And then we evaluate that at 3, our center. So that becomes negative 1. So that tells you a1 is equal to negative 1. Good? Okay. F double prime of x, that becomes positive 2. X minus 2, negative 3. A. And the other side is 2 factorial a2 dot dot dot. And then we substitute 3, so it's just 2, right? And the other side is 2 factorial a2. So that tells you a2 is equal to positive 1 now. Good? Do you see the pattern yet, or should we do one more? Let's do one more. This is negative 3 factorial, isn't it? And the other side is 3 factorial a3 dot dot dot. You know what I'm saying? So if we evaluate this at 3, once again, this always becomes 1. So we have negative 3 factorial. That, and the other side is 3 factorial a3. So that tells you a3 is negative 1. Are we seeing a pattern now? We don't have to find the general term here, but if we had to, what is the general term, an?
Negative 1 to the n minus 1.
N minus 1, or is it n? Oh, let's think about it.
N.
Yeah, we want to start with a positive number, so it's n. So you write n, then you look at it, and you either plus 1 or leave it. That's how we adjust it. Good. Edward, do you have a question?
Yeah, can we do this on tomorrow's test? This like semi-short
Yeah.
way?
Yeah, I relieved you from this burden
Okay.
last week. The reason for that is that AP, this is a pretty, look at the video from second period. There are questions where these formulas come in handy, okay? So it's good to know this technique, okay? So yeah, you can use this, you can actually just purely use the formula too if you want to. And so if you watch that video, then you will see an example how that thing becomes useful, okay? Alrighty. So now, can we write this thing? Now it's first 4 terms, right? Okay, let's do it. I'm gonna push these down. So now we can say f of x, which was 1 over x minus 2, is approximately equal to 1 minus x minus 3, and then plus x minus 3 squared, and minus x minus 3 cubed, and this is 4 terms, correct? Which is not to be confused with the fourth order. You know what I'm saying? Order versus terms, okay? I see 1, 2, 3, 4, and then we cut it off right there. Okay, so that's what prompt A is, and prompt B. Use this result to find the first four terms and general term of the series of ln. Ln. Okay, well, we can just integrate both sides, eh? So if we integrate both sides, this side becomes ln x minus 2 with the same interval of convergence, right? Okay, and that is approximately equal to, and we will integrate with the x minus 3, not x, so this becomes x minus 3, and then minus 1/2 of x minus 3 squared. I forgot the constant of integration, so let me put it at the beginning, okay? C plus, and then the next one becomes plus 1/3 x minus 3 cubed, and then minus 1/4 of x minus 3 to the 4th power. How about that? Good? Say yes. You know what? I'll write it like this, straight equal to and dot dot dot. Because I feel a little uncomfortable evaluating this on both sides when this is an approximation. So this is still 4 terms. You know what I'm saying? Okay, now initial condition at x is equal to 0. Okay, if you plug in 0 here, well, not 0, our initial condition has to be x is equal to 3 in order to kill off all of these. So if I put 3 here, I get ln 1, which is 0, and the other side, all of the terms die except your constant. So that tells you your c is equal to 0. So far, it's been nice, and our c has always turned out to be 0 when we integrate. Don't assume that's always the case, okay? It's usually the case, but you cannot assume such a thing. Whenever you assume, bad things happen, okay? Are we good? So ln x minus 2 happens to be, now we can say squiggly equal to ln, well, x minus 3 minus 1/2 x minus 3 squared plus 1/3 x minus 3 cubed minus 1/4 of x minus 3 to the 4th. How about that? Good? Okay, let's move on. So, okay, and C. We use this to find the computed number differs from ln 3 by less than, okay. So this is where we are doing Lagrange error, seems like, but do we have to use Lagrange error? We are ln 3 over 2, right? So ln 3 over 2, what do we have to substitute here to make this thing 3 over 2? Are we putting 7 over 2 for x? Then we get 3 over 2. You know what I'm saying? You know what I'm saying? Okay. Now, which means our error is at 7 over 2, isn't it? Right? So let's just write it. See, I'm gonna say what ln 3 over 2 is ln, and we evaluate this as 7 over 2 minus 2, isn't it? So our x is, you know what I'm saying? Is that confusing? So we need the error, some unknown n, because we are yet to figure out how many terms we need, right? Wait, Or are we just using number that by less than 0.5? So we have to figure out some unknown n, right? Okay, so unknown n evaluated as 7/2. Now, how do one way is we can do Lagrange error, okay? However, let's just substitute it here, okay? Number one, which term does this error start with? What's the first term of the error? Okay. Let's go back to x. What's the first term of error? My God. Let's review. We're gonna come back to this. Okay, we are saying some function f of x, which is ln, x minus 2, is equal to our nth degree polynomial plus your remainder, correct? Let's back up. Let's really review. God, I can see from your facial expression that you're any infinity. I think we'll use our series as an example. So ours is, oh no, you're killing me. X minus 3 minus 1/2 x minus 3 square dot 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 dot, and whatever this term is, plus or minus 1/n, and then x minus 3 to the nth power, and still plus or minus 1/n plus 1, and x minus 3 to the n plus 1 power, and dot 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 dot. Correct? That's generally how the series look. Say you get this much. This is very concerning. This is what we are calling p sub n of x, isn't it? And what we call the remainder is this tail end of the term. Good? Do you remember forgetting this? So when we say our r sub n of x, that always starts with this very next term. You get it? Or plus or minus. You get it? I'll write one more term. We are in a review mode, so plus or minus. That's ugly, plus or minus. 1/n plus 2, and then x minus 1n plus 2, and then dot dot dot. That's your remainder. Remainder always starts with n plus 1 term. You get it? So one way is to use Lagrange error, because we kind of have the pattern up here, right? You know what I'm saying? But that's a lot of work. Could we do something better than Lagrange error? And then here's the key. We are not finding this at anywhere for any value of x inside the interval of convergence. We are evaluating this as 7/2, aren't we? Hold on, I screwed up. This is minus 3, right? Our center is not 1. For some reason, I changed that to 1. Good. So let's see what happens if we substitute 7/2. 7/2 minus 3. What is it?
1/2.
1/2, isn't it? And the next one is 1/2, 1/2, 1/2, right? So what do you have here? What kind of, this itself is a series. What kind of series is it?
Alternating.
This is an alternating series now, isn't it? Which means we can use alternating series error. You get it? And AP loves this kind of question. You evaluate, you substitute, given X value, and the whole thing becomes alternating series error. And even if we do Lagrange error, it turns out to be exactly the same as this anyway. Okay? Because we are choosing the worst point. Alexandria.
If it's not alternating, is there a way to find the error without Lagrange? Or
No, that's what Lagrange error is for.
okay.
So like we're stuck there, okay? So it's less than that very first term. That's the whole idea. Oh, let me not do that. I'm gonna write it like this. Now absolute value of that thing and lose plus or minus and just put absolute value along like that. Are we good? Now, then we want to make sure this thing is less than 0.05. You get it? So we come back here and say this is less than 0.05. How about that? Somebody punch the calculator and tell me what that n value should be. I'm waiting. And we are recording this, so somebody do it quick before we waste the entire class period. Greater than or equal to?
Two.
2. That's it? Whoa, it happens that fast. Well, that's kind of surprising. Can somebody double check or confirm? Not that I didn't trust you.
It's 2 or greater. Yes.
2 or greater, so 2. Oh, so we only need second degree, not 2 terms, but second degree polynomial to do this. So we need this thingy, and that'll evaluate this thingy that accurately. How about that? You see why error analysis is critical? Because before you start writing the program, if it's 2, then I'm not writing the program. I'll just hand evaluate this. You know what I'm saying? Okay. Any questions on that one? By the way, we know how to evaluate this exactly too, correct? Because we have the function, right? Here, ln. This is our function. So all you have to do is just put 7/2. Okay. Let's look at 57. Okay, we have to write first 3 non-zero terms and the general term, possibly sigma notation of that thingy. So question is, do we microwave or do we start from the scratch? Is the question, isn't it? And then here is error, right? Error meaning Lagrange error, isn't it? Yeah, because we don't know exactly what x is, so although we can kind of get away with the alternating series error, but that's dangerous. So let's just do Lagrange error, meaning you cannot microwave no more. You know what I'm saying? Yeah, microwave, the weakness of microwave technique is quick, but you can't really figure out the error. So doing it the long way, but I hereby relieve you from the burden of doing it long way. And here's a semi-long way, okay? This is what AP does, okay? So you can start doing this, starting on this chapter test. Okay, f of x is equal to 5 and sine x over 2, right? Once you have that, instead of the other side is a0 plus a1x plus a2x squared. We are imagining that part, okay? And then the way we did it was we substitute 0, correct? Once you substitute 0, this thing becomes 0, and the other side a0, right? You imagine that, and then that tells you A0 is equal to 0. You get it? Are you getting this or not? And then you take a derivative. This is a lot less writing because the right hand side is long writing, but that's exactly the same each time. So we have 5 over 2 now, and then sine or cosine. So we'd have cosine x over 2, okay? Then the other side, a1, and then 2a2x, dot, dot, dot. So we substitute 0 there, then we get 5 over 2. So that tells you a1 is equal to 5 over 2. Some people never like this and just say just stay with the long way forever, and that's fine too. Okay. And f double prime of x is equal to, now it turns into negative 5 over 2 squared a sine x over 2. So double prime at 0 is equal to 0, so that tells you a2 is equal to 0. This is our usual sign pattern, so all the even terms are 0. But can you imagine if I taught it like this from the beginning, how confusing that would be? Right, that was the reason that I didn't allow this, but now I think you're mature enough to do this, or not. Okay, the next one, negative 5 over 2 cubed cosine x over 2. So substitute 0 there, and then you have negative 5 over 2 cubed, right? So that tells you a3 is equal to 5 over 2 cubed, and then there's 3 factorial, right? Because the other side is 3 factorial a3 and dot, dot, dot. Are you with me? You want to do more, or do we see the pattern? I think we have done this enough to see the pattern now, right? So we can say dot, dot, dot this way, and f to the nth derivative of x, and this will be either plus or minus, and we still need that 5 and 2 to the nth, right? And this term is either sine or cosine. Good. So regardless, that tells you an should be plus or minus 5 over 2 to the n and to factorial that over 0, right? Depending on whether that n is odd or even. You with me? Say yes. Okay, then let's write down. This is where I screwed up on Dropbox note. So your f of x is equal to, now we can say 5 over 2 x minus 5 over 2 cubed 3 factorial x cubed plus, and then 5 over 2 to the 5th power and 5 factorial x to the 5th and dot, 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 right? Okay, and this general term is where I screwed up. I'll just put it in sigma, might as well, right? So this is sigma of n starting from 0 to infinity of, and then we're going to need something like this, and then we need 5 over, and then this we have to put even number terms, so 2 to the 2n 2n plus 1, like that. You get it? And then 2n plus 1 factorial, then x to the 2n plus 1. How about that? Let's check. So if I put 0, then this becomes 1, this becomes 1, this becomes positive, we're good. Are we good? You with me so far? Okay then. Now we have to do ratio test. So this is part B. And you use this thingy to do the ratio test. Okay? Moving on. So part B. Let's do a ratio test. Limit of n approaching infinity of, and that thingy, 5, and I'll just put x here, 2n plus 1 over 2n plus 1, 1, and then 2n plus 1 factorially, like that, eh? Okay, and then on top, 5, x to the 2n plus 3 now, right? Over 2 to the 2n plus 3, 2n plus 3 factorial. This is a correct ratio test, although if you just put the very next term, it still works anyway. So it gives you exactly the same thing. Limit of n approaching infinity of, now this thing, 5's cancel, so simplifies to this x squared here. And then the denominator is kind of lengthy, so we need 2 squared, and then 2n plus 3, and then 2n plus 2. Is that how the factorials simplify? And nevertheless, this thing approaches 0, which is less than 1 for all x values. So our interval of convergence happens to be infinity to infinity. How about that? Good. Now let's do part C, Lagrange error. Since x varies from -2 to +2, and this is where you have to be careful, your Lagrange error, which is also known as this, right? Real minus the approximation. Good. This is AP's notation. Now this will be f evaluated n plus 1 derivative evaluated as c over n plus 1 factorial x to the n plus 1a. Okay, and this thingy somewhat looks like this, and the next term looks still somewhat like that, except 2n plus 1a. We can still find the upper bound of 1 sine and cosine, so we'll have 5 times 1, if you will, and then over, and then you need 2 to the n plus 1 here, and then n plus 1 factorial, eh? Say yes. And your x is 2 to the n plus 1. How about that? Or negative n plus 1. But we are taking absolute value. Okay? And you want this to be strictly less than 1, eh? Say yes. So how many terms does it take? Well, there's no other way but just playing with a calculator, and then it takes 3 or more terms to achieve that kind of precision. Anybody lost? Which means this is not 3 terms, it just means third order, so I'm supposed to take those 2. I'm just going to use copy and paste tactic if it works. Let's try that one more time. And then let me paste it here. So my f, and then change that to approximately equal to. That's my f. You get it? Say yes. Okay, any question before I do 59 then? Okay, and 59 looks like we are looking for, what do they want? Radius of convergence? Interval of convergence? Somebody tell me what they want. I'll just start doing ratio test. What was it?
Interval and ratio, let's do both.
Oh, both. Okay. I mean, if we do the interval of convergence, of course, we know the radius of convergence as well, right?
Yeah.
Yeah, interval of convergence, that work includes the radius of convergence. So let's take a ratio test. So we have x to the nth power, n to the nth power over n factorial. Ooh, okay. This doesn't look good, right? It's got to have tiny, because n to the n grows quite fast, right? N to the n wins this race against the factorial. This is the only thing that grows faster than factorial to my knowledge. Meaning that interval of convergence either is zero, I mean the radius of convergence either is zero or it's got to be very tiny to offset this numerator growing faster. You know what I'm saying? So how tiny do we want it? Can you feel like this? So here then you have x to the n plus 1, n plus 1 to the n plus 1 over n plus 1. Oh, I wish I'd given myself more space, but I think I managed to squeeze it in. Like that, eh? Okay, let's see how that simplifies. You know what? I hate it. I'm gonna give myself more space. I always do this to myself. Okay, let's see. I think I can make this numerator bigger, eh? What do you say? Yeah, see, infinitely prettier, isn't it? Yeah, let's do that. Can move this far up a little bit. Wow, so much better. Okay, this is equal to limit of n approaching infinity of. Now, let's see the numerator, n plus 1, right? Right, let's take it one step at a time, okay? The factorials give you n plus 1 in the denominator, right? Let me plug in my computer, it's about to die. While I'm at it, I will plug in my other computer that's also about to die. One sec. Okay. So the denominator has n plus 1. Okay, that's just from canceling factorials. So far, so good. And then let me write what's left, and then hopefully you will recognize it. Here's n to the nth power, and then here is n plus 1 to the n plus 1 power. Good. And then I have x. Like that. Are you with me so far? Okay. Now let's go down this way, limit, and approaching infinity. Do you see that one of the n plus 1 cancels now? Right, so what we have is n plus 1 over n quantity to the nth power. Is that too much algebra, or do you see that much? Do you recognize that thing? Let me tweak it just one more time, so hopefully you will see it. And approaching infinity of 1 plus 1 over n to the nth power. Now, do you recognize this thing? What is this thing with the limit? Say it.
Was it
Say
E?
it. That's E, isn't it? Okay, those of you who don't recognize that, would you like to review and find out how to get that limit? Show virtual hands if you want to see that. This is chapter 8. Okay, let me show you. I'll do that with green. So on a side, let me just evaluate that limit. Limit of n approaching infinity of 1 plus 1 over n to the nth power. Okay? Now we take giant E tactic. So this is giant E followed by ln, and then 1 plus 1 over n. To the nth power here, we can at least write it like that, eh? Say yes. Okay, but then we have to tweak it one more step, because what we have is, see, this thing approaches 0 as n approaches infinity, so we have ln1, which is 0, so we have infinity times 0. So we cannot localize it quite yet. So n approaching infinity of e to d, so let's write it like this, ln 1 plus 1 over n over 1 over n. You get it? Now this thing was approaching 0 and this thing approaches 0, so we can localize it. So limit n approaching infinity of e to d. Let's do the denominator first. That is -1 over n squared. And the numerator, I'm going to zoom in. So you'll have 1 plus 1 over n. And then the chain rule, that's just same thing as this, so recycling our work. Good. And those things cancel, so we have limit n approaching infinity of e to d 1 over 1 plus 1 over n. Still with me? And take the limit, this thingy dies, so we have e. How about that? Okay, it's a handy thing to recognize, so that thingy is e. Alrighty, so let's do that equation here. We want this thing to be less than 1, correct? Right, that means absolute value of x needs to be less than 1 over e. So this is your radius of convergence. You get it? You get it. This right here is your radius. Let's just write C. Okay, then the boundaries, right? What that means is it's between 1 over e and -1 over e. Good? Okay. Did you say that they want interval of convergence as well?
Yeah.
Okay, let's do it. So we go here, boundary. At x is equal to 1 over e. Let's plug it in to original. So if we put 1 over e, what does that thing become, right? Okay, let's see. This is a lot more headache than I was hoping for. And approach this thingy from 1 to infinity. I'm looking at the other screen to copy this thing. So I can put e down here, e to the n, it's 1 over e, and then n to the n, and then I have n factorial is what I end up. Correct? Holy cow.
Actually, Mr. Kim, I looked at the book. They don't want the interval. They only wanted radius.
Okay, thank God.
My bad. I apologize.
Yeah, it's okay, because this is turning out to be a headache. I mean, if I had to do it, I was thinking along this line. But then you see, that's kind of headache now, isn't it? Yeah, so, okay, well, give up really fast. Okay, and then, what else do they want?
Lagrange error for the f of -1 over 3 with the third order.
Okay, Lagrange error. Let's calculate the Lagrange error, okay? So let's write these terms out. That thingy, I'm looking at the other screen to write that thing out. And let me know if I screw up. So Lagrange error is this. I'm gonna do that with black. So f of x, or f of -1 over 3. Okay, that would be negative 1 over 3 plus negative 1 over 3 square, and then 2 square over 2 factorial, eh? Plus negative 1 over 3 cubed, and then 3, this is x, you know what I'm saying? That 3 is ugly. 3, and then 3 cubed over 3 factorial, eh? And then plus, what order did they say?
They said they wanted the error for third order.
Third order. So this is it. This is the approximation, isn't it? And the Lagrange error will be the very next term that's about to come here, correct? So let's write that down here. So our Lagrange error are 3 at x, just let's conveniently not write anything. Now that's approximately equal to, we don't know what the next term where we are evaluating. We could evaluate, actually I'll just write it. That is the absolute value of the next term, x. Instead of x, we're supposed to use c to the fourth power, and then 4 to the fourth power over 4 factorial. Correct? Say yes. Say yes. So in order to maximize that, we are just using 1/3 here, correct? Absolute value of 1/3. Okay. So that is, so if I put 1/3, I'll just write it. 1/3 negative, but absolute value of fourth power, 4 to the fourth power over 4 factorial, like that, eh? And what is that number? It's 4/3 to the fourth power over 4 factorial. Can somebody punch the calculator quickly and let me know what this number is? Oh, come on, people.
Approximately 0.131687.
131687.
87.
Okay.